Now we will discuss about refraction of spherical surfaces. Here we may consider a part of a spherical transparent surface to be almost planar, and just at a point on such a surface we can apply laws of reflection and the image of the object can be traced. So using our geometrical method, we are going to find out the relation between object distance, image distance and radius of curvature. When I say spherical surfaces means, here I show you a thick sphere. You can see it. This is like a transparent thick sphere. You can see that how the magnification is. So it is a curved surface here. Here is also a curved surface here. So we can consider this as a thick lens. Similarly, you might have seen a thin lens. So this is a thin lens. You can see how the curved surfaces are. First, we will derive equation for refraction at a single curved surface as it is shown to you. Later, we apply the same formula for deriving the lens formula of a double convex lens, which is a thin lens. Okay. Now, let us take, this is the curved surface and this is a glass medium. And here be the point center of the surface, geometrical center. We consider that almost something like pole, as we discussed in the case of mirrors. And let us say this C is the center of curvature of this curved surface. You know that this line joining this is the axis of the curved surface. Now extend this axis. Let at some point there be an object move. Consider a ray incident at some point. Let us call it as N. Now imagine a normal drawn from N to the axis means almost very nearer to the M. So this MN is almost equal to the perpendicular distance from N to the axis. Now we know that the line joining N and C, that is, this is the normal at N drawn to the surface. You can imagine a tangential plane here for which NC is the perpendicular. Therefore, this is the angle of incidence. Now, after refraction, the ray bends towards the normal because this is a denser medium of, say, refractive index N2 and this is N1. Therefore, when the ray enters a denser medium, it bends towards the normal. Therefore, this must be the angle of refraction. Angle made by refracted with the normal is angle of refraction. Now, from the geometry of the figure, I can write like this: tan of angle NOM. So I am taking a triangle here. So almost you can represent this as perpendicular. So in such case, this is MN by MO. Similarly, if I will take this triangle, here this is the image. So NCM. So tangent of NCM. So this is equal to again MN by MC. Similarly, angle NCI. So NIM. So tan NIM. So that is equal to again MN by MI. Now, let us apply Snell's law to this case. So according to which N1 sin I is equal to N2 sin R. So this is N1 sin A is equal to N2 sin R. Here we take approximation of the angles are very small. In such case, this can be written as for small angles of incidence and refraction angle also is small. Then this is equal to N1I is equal to N2R. But I is the external angle. You can observe that. So here is the triangle NOC. See, this is NOC. For this, I is the external angle, which is equal to sum of opposite interior angles. Therefore, I can write like this N1. This external angle is equal to angle C plus angle O. So angle C plus angle O is this one. So that is N by this angle plus this angle. MC plus Mn by Mo. That is equal to angle R. So here angle R, now you can consider this is a triangle here. So this is internal angle. So this angle minus this angle will be this one. Same principle I am using. So N2 is equal to N2 into, in the place of R, I am writing this angle minus this. So that is Mn by MC minus Mn by Mi from this. So Mn gets cancelled on both sides. Then what remains? N1 by MC plus N1 by Mo is equal to N2 by MC plus minus 1 N2 by Mi. So let us take this N1 by MC to that side and then that N2 by Mi this side. So I can write like this N2 by Mi plus N1 by Mo is equal to, if you take this N1 to that side, it will be minus. So this N2 minus N1 by MC. Okay, this is what we got. So let us call it equation. Same one. Now let us substitute the symbols for all this. What is Mi? What is MC? We know that MO is the object distance U, and MC is the radius of curvature of the curved surface, and this Mi is the image distance. So let us use those symbols here. N2 by D plus N1 by U is equal to N2 minus N1 by R. Now let us use the sign convention. So here V is the image distance. So you are measuring the image distance in the direction of the ray. So therefore that is positive. And here then U that is MO is measured in the opposite direction of incident ray. Therefore it is negative. And radius of curvature again measured in the incident ray direction. Hence it is positive. Therefore N2 by V minus N1 by U is equal to N2 minus N1 by R. So this is the formula relating the refractive indices of the media and object distance, image distance with the radius of curvature.